All right, everybody, let's take a look at these questions covering Kepler's laws and Newton's gravity. I've got my equation sheet handy, so I can pull that up. The two main equations we'll be using here are Kepler's third law, that's this p squared equals a cubed, and then Newton's law of gravity here. All right, we'll be using those two equations. But let's take a look at each of these and see if we can figure them out. So let's start with question one. Here we go, Q1. All right, it tells us, actually it asks us, what is the orbital period in years of a planet with a semi-major axis of 10 AU? So it's asking us to find orbital period. So I'm just going to write P equals question mark. That's what it's asking us to find. And it gives us a semi-major axis. A equals 10 AU. All right, so I want to find an equation that's got those two things. In this case, I know that's going to be Kepler's third law here, p squared equals a cubed. Now from here, there's a couple different approaches you could take. I mean, you could just plug in 10 for a and kind of work your way through it. The good little scientist that I am, I was always taught that first thing we should do is solve for the variable. After all, we want to use all that math we were taught a long time ago in algebra class. Maybe you don't want to use it, but we're going to use it. So I'm going to solve for p because that's the thing I want to know. And to solve for p here, I need to take the square root of both sides to get p unsquare rooted. So what that means here is that p is going to equal the square root of a cubed. All right, that's how I would solve. Now, this equation is always going to be true, by the way. I mean, you could write this equation right on your equation sheet, because if you're ever solving for the period, the orbital period, you can use this equation. It's always true. All right, so now we can actually plug in our value of a here, 10 AU for the semi-major axis, and we would get this, that the orbital period is going to equal the square root of 10 cubed. All right, and this is where we can get out our calculator. So I want to find the square root of 10 cubed. Now, depending on your calculator, you're going to want to find like the right buttons to push, but I'm going to write it like this on mine. I'm going to type square root, and then I'm going to do parentheses 10 to the power of, that little caret means raised to the power of 3, close parentheses. So that's how we say 10 cubed, right? And enter. And I get an absurdly long number. I only need the first few digits here. So the period is going to be 31.62, let's say. All right? So 31.62. The period equals 31.62, and that's going to be in years because the distance was in astronomical units. Okay, so that should be my answer for, I'll just write it up here. Why not? Well, I'm just going to delete it anyways. Okay, so that's Q1. Great. Let's take a look at question 2. I'm just going to scroll down a little bit here. All right, now question 2 is asking a similar question, although a little different. Let's take a peek. Q2. It says, what is the semi-major axis of a planet with an orbital period of 25 years? So we're being asked sort of the opposite question here. So what is the semi-major axis? So A equals question mark of a planet with an orbital period, P equals 25 years. So we're going to use the same equation, Kepler's third law, to solve this. P squared equals a cubed. Except this time we want to rearrange this equation to solve for the semi-major axis, A. Now, it may have been a while since you learned this, or maybe so long ago you've forgotten. I would certainly understand that. To undo something being raised to the power of 3, you have to do something which is called the cube root. Okay, the cube root. And the cube root is the same as raising something to the power of 1/3. Okay? So that's how we might end up, whoop, that's off the screen. That's how we might end up typing it in our calculator, in the same way that a square root is the same thing as raising something, there's caret, raising something to the power of 1/2. All right, that's how we will type the cube root into our calculator. But first, let me just write it out. Just delete that so we don't run out of space here. All right, it's a slow way to delete, but there you go. All right, so I want to rearrange this equation. What I need to do to get a by itself is take the cube root of both sides, which means I'm going to end up with here the cube root of p squared. P squared, the cube root. All right, so now I'm just going to flip sides here so it's easier to write. I'm just going to write a equals then the cube root of 25 squared. Oh boy. Now when I type this into my calculator, I'm going to write it like this. I'm going to say parentheses 25 caret 2. That's 25 squared. And then I'm going to close that parentheses and then say caret 1/3. Right? That's how I'm going to take, not 1/3, but 1 divided by 3. Okay? That's how I'm going to take the cube root. So let's do that. Okay, I'm going to clear my calculator. Start with the parentheses. 25 caret 2, close parentheses, that's my 25 squared, to the power of 1 divided by 3. Enter. All right, and I end up with a semi-major axis of 8 point, we're just going to take the first couple numbers here out of this huge string, 8.55, let's say, just rounding, 8.55 AU. All right, so there's my answer for question 2. Now, just like before, this equation we used here, right here, where we solved for the semi-major axis, you could write that right on your equation sheet, right? So that you don't have to do that step of algebra every time that you solve a problem like this. In fact, I would encourage you to do that. Okay, now let's move on to some gravity problems. I think these are some of the hardest in the whole class, so certainly don't feel bad about that. Because certainly the equation is the most complicated, but we'll figure it out. It says, what is the force of gravity acting between the Earth and a 100 kilogram person standing on the surface of the Earth? So it's asking about the force of gravity. You'll see all three of these do. So I know what equation I'm going to use. And we might just start by writing that equation. So here's Q3. I'm going to start by writing the equation here. Force of gravity equals G, which is the gravitational constant, times big mass, the mass of the large object, times small mass, the mass of the small object, divided by r squared, which is the distance between them squared. So let's just start writing what we know. In this case, we're trying to find the force of gravity, trying to find F. So we don't have to actually do any algebra. We don't have to rearrange this equation at all. What we do have to do is make sure we're plugging in the correct values for each of these. So let's start with G. G is a constant, and it's on our equation sheet. It's 6.67 times 10 to the minus 11, and then there's a bunch of units on it. Now this constant only works if the mass is in kilograms, which it always will be, so you don't have to worry about that, and if the radius or distance, I'll say, is in meters. And that will not always be the case. I might sometimes tell you that the distance is in kilometers, or I might give you a distance in astronomical units. And you're going to have to make sure that the distance you're plugging into the equation is in meters. Okay, so let's keep going here. That's our gravitational constant. The big mass is the mass of the Earth in this case, because this is the gravity between the Earth and a person. The mass of the Earth is given on our equation sheet. So let's pull that up here, down here, m Earth, 5.97 times 10 to the 24. See if I can remember that. Okay, 5.97 times 10 to the 24 kilograms. The small mass is the mass of this person. which it says is 100 kilograms. And the person is standing on the surface. Now, whenever we do a calculation like this, the distance we use is from the distance of the center of those objects. So if here's the Earth and here's a person standing on the Earth, the distance we use here is not 0 because they're standing on the surface. Instead, it's the distance from the center of the object. All right, so in this case, we'd actually have to use the radius of the Earth as our distance from the center to the surface, the radius of the Earth. So our R value is actually going to be the radius of the Earth, which is also given on our equation sheet. Radius of the Earth is 6.37 times 10 to the 6 meters. 6.37 times 10 to the 6 meters. And with that, we actually have everything we need to solve this problem. We just have to plug in these values. But since a number of these values are written in scientific notation, we're going to want to be kind of generous with the parentheses that we use as we type this in to our calculator. Now, when I type it in, I'm just going to write it down. Should I write it down? I guess I'll write it down. So when I type this in, I'm going to type in here, I'm not going to type F, but that the force is going to equal, I'll write it probably like this. I'll probably just put parentheses around every one of these. I don't have to, but it's really going to make sure that these aren't getting mixed up. 6.67 times 10 caret, I'll just write caret, minus 11, close parentheses. That's G. I'll write times, and then I'm going to go off the screen, so I'll put it down here. Times what? Times the first mass, 5.97. You get the idea. Times 10 to the 24. Okay, so you're going to put all that in the, let's just put it right into the calculator. All right, rather than writing it over again. Okay, here we go. So the force is going to be, parentheses, G, 6.67 times 10 to the negative 11, close parentheses, times big mass, 5.97 times 10 to the 24. Oops, I forgot parentheses. Again, I'd probably be okay, but just to be safe, I do like having those parentheses there, particularly when we get to squaring our distance. We're going to need them. So, okay, here we go. That's the mass of the Earth times 100. Now I'm going to say divided by, and now this is really important to have parentheses here. Parentheses, I want my distance. And I have to have that parentheses because when I square it, I want to make sure I'm squaring all of that distance. So let me get the value here. Let's see, the distance is 6.37 times 10 to the 6. So divided by 6.37 times 10 to the 6, and then squared. This is really important right here. The entire distance should be inside these parentheses before it's squared. Okay, that's our distance that we're using. You'll see that again in the next problem, I think. All right, and then I hit enter. There we go, 981.3. Okay, we can ignore all the other digits. 981.3. Great. So this force of gravity is 981.3, and the units are newtons, although you're just going to type the number into here, 981.3. Okay, cool. Not so bad. I mean, considering this is like the hardest math we're going to be doing, that's not so bad. Let's take a look at the next question. Q4. The force of gravity, here we go. What is the force of gravity acting between the Earth and a 60 kilogram person who is 400 kilometers above the surface of the Earth? So this is similar to the last problem. I have the Earth, but now instead of standing on the surface, this person is 400 kilometers above the surface. All right, maybe in outer space or whatever. So when I consider the distance is going to have to be the radius of the Earth. There's the radius of the Earth plus 400 what? Not meters, 400 kilometers. So actually that's going to have to be adding 400,000 meters. So the trick here is going to be making sure I get the distance accurately. Okay, so again, our equation is going to be force equals G times M over distance squared. G doesn't change. That is 6.67 times 10 to the minus 11. The big M is the same as our last problem. It's the mass of the Earth. I'm just going to pull that up again here. From my equation sheet, it's 5.97 times 10 to the 24. 5.97 times 10 to the 24. The small mass is now a 60 kilogram person. 60 kg. And the distance now is the radius of the Earth plus 400,000 kilometers. So let's write that down. Radius of the Earth is given to us 6.37 times 10 to the 6. 6.37 times 10 to the 6. And now I'm going to plus 400,000 meters. Now in scientific notation, that is 4 times 10 to the 5. Okay, but you could just write, you could use that, or you could just say plus 400,000. That's fine. Our calculator understands that. Okay, and that'll give us our distance in meters. So it's going to be really important that when we do r squared here, we put all of this in parentheses before we square it, you know? And then we square it. Because this represents the distance. Okay, let's plug in those values. And again, instead of rewriting all those numbers, I'm just going to go right to my calculator. All right, let's clear this out. So here we go. Up top, I've got 6.67 times 10 to the negative 11, parentheses, times the big mass of the Earth, is, parentheses, 5.97 times 10 to the 24, close parentheses, times the smaller mass. In this case, that is 60 kilograms. All right, and now divided by parentheses, I've got the radius of the Earth, 6.37 times 10 to the 6 times 10 to the 6 plus 400,000 close parentheses squared. Now, as you can possibly imagine, you know, if you're getting this wrong, the chances are that you're typing it into your calculator incorrectly, because you see there's a lot of carets and parentheses, and so that could be where things are going wrong. So you want to double check, make sure you have what I have here, and hopefully what I have here is correct. I think that's the right answer, 521.28. 521.28. Great. So again, that's in newtons. So the force equals 521.28 newtons. Remember before when the person, well, it doesn't matter. It's interesting to see how it's gone down, but the mass of the person also went down. So I guess it's not like a fair comparison, but 521. Okay, cool. Let's take a look at the last one. The force of gravity acting between the sun now and an 80-degree person who is 0.8 astronomical units away from the sun. All right, so now this person is just floating out in space. Here we go, Q5. Same equation, F equals GMM over R squared. The difference here really is going to be in the values, but finding out R is just a touch tricky here. What is the distance? It's 0.8 AU, but we have to put that in meters, right? So, well, let me just write that down here. Remember, we can get this from our equation sheet as well. 1 astronomical unit is 1.49 times 10 to the 11 meters. So 1.49 times 10 to the 11 meters. So then how much is 0.8 AU? Well, I don't know. The way you figure that out is you just you put some parentheses around there, you say 0.8 times 1.49 times 10 to the 11. It's that many meters. You just take 0.8 times 1 AU, and that's how you can do it. You could do that if this was 2 AU. You just take 2 times 1.49. But you want to include that inside the parentheses, because if you're going to square it, you need that inside the parentheses. Okay, we're going to use that in just a minute. G here, okay, G is 6.67 times 10 to the minus 11. You might start, you just remember that number now for the rest of your life. I know I do. I did so many of these kind of problems when I was studying astronomy that if you just stopped me on the street and said, hey, what's the gravitational constant? I'd be like, oh, it's 6.67 times 10 to the minus 11. Maybe you'll get there too. I don't know. I don't know if you want to get there. Okay, the mass, now the big mass is the mass of the sun. So that's also on our equation sheet. 1.99 times 10 to the 30. 1.99 times 10 to the 30. All right, the little mass is now 80 kilograms. Okay, and then now our distance is this 0.8 AU, which we said is this. It is 0.8 times 1.49 times 10 to the 11 meters. So again, when we put this in, we're going to put that whole thing in parentheses before we square it. All right, let's get our calculator and finish this up. So what have we got? Parentheses, 6.67 times 10 to the negative 11 times 1.99 times 10 to the 30. What else? Okay, times the smaller mass, times 80. Now divided by parentheses, and we have 0.8 times 1.49 times 10 to the 11, close parentheses, square. Now, if we get a crazy big number or a crazy small number, like in scientific notation, I'm sure we did something wrong, but if it's, nice, it's a simple number that we could type into the box, like 0.747. All right, 0.747. So the force is really quite small. 0.747 newtons. All right. Well, I hope that made some good sense as we went through those problems. And of course, as always, if you have any questions, feel free to reach out.